So am I audible to all of you? What happened? Why you are giving your attendance now? Yeah. Bibrajit, what happened? I haven't asked for your attendance, right? I'll mark you absent today. That's fine. Please don't act over smart. Just in the starting of the class, you are just coming and giving your attendances. You are not responding anything. Unmute yourself and give me the reason, Bibra. What happened? Yeah, please unmute yourself and give me the reason why you are giving your enrollment number now. Yeah, hello. He will be marked absent. Just inform him. Or he should give me a reason or why has he done this kind of things. I'm asking every one of you after the end of the class, you'll have to give the attendance, not now. Can you all see my screen? Yes. So in the last class, we discussed regarding slope and deflection. So today we will be discussing what? Torsion. Am I audible to all of you? I hope I am audible to all of you. Yes, please. Okay, fine. So what we shall do is look at torsion. What does torsion means actually? I'm giving you a practical example initially. Suppose you all wash your clothes, right? So while washing your clothes, so as to drain out the water after washing your clothes, what you do? You just try to coil it. Suppose you are washing a towel. So what happens? In order to in order to drain out the water, if it's a big towel, what you do? You just twist it. Yes or no? If you twist it, then there is certain form of twisting motion. So that is basically called as what? Torsion. I hope this is clear for all of you. I hope this is clear for all of you. Yes? Any doubt? So, what is the difference मतलब? किसका difference? मैं torsion का बात कर रहा हूँ और मैं torsion का बात कर रहा हूँ कि torque का बात कर रहा हूँ? हाँ? मैं torque की बात कर रहा हूँ कि torsion का? मैं torsion का बात कर रहा हूँ कि torque का? वो बोलो तो? Yeah, I am talking about torsion, right? So why do you ask something else? I'll tell you about it. Let it get finished, right? Yes or no? Huh? Yes or no? Torque and torsion are totally different things. Huh? Torque is related to something, angular acceleration, and this torsion is what? It is just the rotating portion. Again, someone is giving the attendance. This is very much disturbing. Akam. It's very much disturbing. This will be marked absent. I am assuring you that. देखो मैं एक बात बोलता हूँ distortion is suppose a body is clamped at one end. That means what? It is fixed at one end, right? And then it is twisted at other end. So a torque T equal to F of D is applied. Now look, now you come to the topic. Now I was talking about torsion, I give you the basic concept. That phenomenon is called torsion. But torque is what? It is the measure of the turning effect. It is given by F into D. Turning effect means what? Suppose this is something. Now once you apply here, it will rotate like this. No? So that measure of the turning effect or the angular acceleration is known as torque. Okay, so this is the difference between torque and torsion. Are we clear here? Hello? Are we, are we clear here? Okay. Now, what is the effect of torsion? Now, effect of torsion load applied to a bar are to impart angular displacement at one end cross section with respect to the other end. This angular displacement you can say as torque. Now, that means what? If it is rotated at one end, what will happen? That angle of twisting will be there, no? So that is known as torsion. Then you can write to set up shear stress on any cross section of the bar perpendicular to its axis. Okay, so these are what? These are the two, effects of what? Torsion. Okay. Now, generation of shear stress. Now, if you see this figure just now I told you now, it is fixed at this side. It is what? It is fixed at this side. Now, if it is fixed at this side, and eventually you apply what? You apply this twisting moment on it, then it will continue to rotate on the other side, right? So in this way, what will happen? There will be deformation, and that deformation will be what? It will be a shear deformation. Okay, I hope this is clear. There will be a deformation, and that deformation will be a shear deformation. Okay, so this now, if you want to know what is meant by a shaft, if you want to know what is meant by a shaft, huh? A shaft means what? These are machine elements which are used to transmit power in the machines. Fine. A shaft is a machine element used to transmit power in a machine. Now the twisting moment for any section along the bar is defined to be what? The algebraic sum of all the moments of the applied couples that lie on one side of the section under consideration. That means what? a twisting moment. Suppose a bar is twisted. So if it is twisted, then there will be what? A large number of couples will be there. Hmm. So if you consider all the couple, and you know add all those couple, then that is called what? The twisting moment for any section along the bar. Couple means what? We discussed in engineering mechanics also now last semester. Force into what? Perpendicular distance. Okay. Now, what is shearing strain? If a generator A and B is marked on the surface of an unloaded bar, and after the twisting moment T has been applied, this line moves. Now, once you twist it, then what happens? Suppose a particular end is fixed, but there is what? Shear. And now the shearing strain means what? Change in the original value, and you have to that will be in the denominator, and in the up it will be what? The original value minus the final value. So in that way, we will consider it as shear strain. The shearing strain is nothing but simple shear strain. And modulus of elasticity in shear means what? The ratio of shear stress to shear strain, or it is called what? Modulus of rigidity. No, or angle of twist. Now suppose that that bar or shaft, which is being twisted, you know, that angle through which it is being twisted is called as angle of twist. Now this relationship of torsion, tau by j, t by j equal to tau by r equal to g theta by l. This relationship is very important. Okay? Let's try to remember this relationship. And here are what the first term, second term, and third term describes basically. Okay, this is the expression for actually torsion. Is it okay for everyone? These three people won't be getting their attendances today. Okay, I'll mark them absent since they have not listened to me anything and just entering, giving the attendance and leaving. This thing won't work. Okay, I I'll mark them as absent. Okay. So Let us do one thing now. What we will do is, let me show you some conceptual videos. First of all, let's clear your concept of shear stress and shear strain. Then we will go to the next video of what, torsion. I showed you this one before also, I think. Seems like you have all forgotten about it. Okay, let's start.
What really happens when we cut a cake using a knife? In physics, we could say that the cake experiences stress. Usually, when we cut a cake, we hold the knife straight and apply the force perpendicular to the surface area. So, can you guess what type of stress this is? It is normal stress as the force is acting perpendicular to this area. But what about these cross-sectional areas of the cake? The area on top is not the only area that experiences stress. As we pierce the knife in, this cross-sectional area experiences stress too. It doesn't look too obvious, but it does experience stress. We can also see that the force is not perpendicular to this area. It acts parallel to it as we are pushing the knife straight down. If the force acts parallel to the surface, it exerts shear stress. This stress tries to push the two surfaces away from each other and hence results in plastic deformation. So this is the basic difference between normal stress and shear stress. Normal stress is where the force is acting perpendicular to the area of contact, while shear stress is the force that acts parallel to the area. Let's take another example which explains shear stress better. Here's a beam and assume that it's fixed at its base. If we apply normal force to this cross-sectional area, then we know that the stress experienced by the beam will be normal stress, which is simply given by F over A, where F is the applied force and A is this cross-sectional area. This will result in a normal strain in the beam, which is given by delta L over L, where delta L is the change in length and L is the original length. Now suppose that we apply a force in this direction, parallel to area A. Again, the beam will experience some stress, but this time it will be a shear stress. The equation or formula for shear stress is the same as that of normal stress. Stress is simply the applied force per unit area, whether it's acting perpendicular or parallel to the area. What about the deformation in the beam by shear force? Here the deformation will be something like this. The object is stretched to some extent. Note that the beam is fixed to the base, so this cross-sectional surface will remain where it is, whereas the cross-sections above it will all get displaced to the right by increasing amounts. Now look at the maximum displacement here. Let's call it delta x. We know that this length is L. It's perpendicular to this. Also notice that there's an angle formed here. We can call it theta. With this information in place, let us define what shear strain is. Shear strain is simply equal to tangent of theta. Yes, shear strain is simply the tangent of this angle. But what is tan theta? We know that it's the opposite side over the adjacent side. Here, the length of the opposite side of theta is delta x, and length of adjacent side is L. So it's equal to delta x over L. So that's how shear strain is defined. Length of the deformation at its maximum over this perpendicular length.
Okay, so this shear stress and shear strain concept is important so that you can revise and you can understand torsion much better, because the shear stress and shear strain is directly related to what is torsion. Now let us understand torsion much better as per my explanations. Okay.
Torsion is the twisting of an object caused by a moment acting about the object's longitudinal axis. It is a type of deformation. A moment which tends to cause twisting is called torque. A common example of an object subjected to torsion is the transmission shaft, which is used to transmit power by rotation. This could be the drive shaft and axles, used to transmit power from the engine of a car to the wheels, for example, or the shafts used to transmit power from the blades of a wind turbine to its generators. Let's explore what happens when we apply torque to a circular bar. We can see that the applied torque causes the bar to deform by twisting. An interesting thing we can observe is that individual cross-sections of the bar do not get distorted by the twisting. We can imagine that the bar is made up of multiple individual discs, which rotate relative to each other when the torque is applied, but do not deform. This is only true because the cross-section of the bar is axis symmetric. A bar with a rectangular cross-section is not axis symmetric, and so torsion results in warping of the bar cross-sections. This warping is complex, so in this video, we will keep things simple and only consider torsion as it relates to circular bars. Let's fix our bar at one end, and track how a line between point A and point B deforms as we apply a torque to the other end. The applied torque causes the free end of the bar to rotate by an angle phi. This is called the angle of twist. It varies linearly from 0 at the fixed end of the bar to phi at the free end of the bar. We can calculate the angle of twist using this equation. It is a function of 4 parameters: the length of the bar, L, the applied torque, T, the shear modulus, G, which is material property, and J, which is the polar moment of inertia. So, what is the polar moment of inertia? It defines the resistance of a cross-section to torsional deformation, due only to the shape of the cross-section. The polar moment of inertia for a hollow bar, with an outer radius RO and an inner radius RI, can be calculated using this equation. Setting the inner radius to 0 gives us the equation for a solid bar. One neat thing about the equation for the angle of twist is that it gives us a way to determine a material's shear modulus, G, experimentally. If we apply a known torque to a bar of known length and cross-section and measure the resulting angle of twist, we can use that information to calculate the material's shear modulus, G. Torsion generates stresses and strains within the bar, which we need to be able to calculate so that we can make sure our bar won't fail. To figure out how to calculate these stresses and strains, we can start by observing how a small rectangular element on the surface of our bar deforms. The element is initially rectangular, but when the torque is applied, it gets distorted. Let's take a closer look. Because the bar is axis symmetric, we know that individual cross-sections will rotate but won't get distorted. So the sides CF and DE of the element will only move vertically along the lines shown here. After the torque is applied, the angles of the element are no longer 90-degree angles. This gives rise to a shear strain, which corresponds to the angle you can see here. We can calculate the shear strain by considering only the geometry of the bar in the deformation. It corresponds to this angle between AB and AB prime. We can use trigonometry to derive an equation for shear strain. For small angles, gamma will be approximately equal to the tangent of gamma, which makes it equal to the length BB prime divided by the length AB. AB is the length L of the bar. We can calculate the length BB prime by realizing that it is the arc length of a circle with a radius r, covering an angle equal to the angle of twist, theta. So the shear strain is equal to the radius of the bar multiplied by the angle of twist divided by the length of the bar. This is actually only an equation for the shear strain on the surface of the bar. But what about inside it? It turns out that the shear strains increase linearly with the distance from the center of the cross-section. So if we define ρ as the radial distance from the center of the cross-section, we can replace r in this equation with ρ to give us an equation we can use to calculate shear strain due to torsion at any point within the bar. That's shear strains covered. But what about shear stresses? Like the shear strains, shear stresses increase linearly with the distance from the center of the cross-section, with the maximum shear stress occurring on the outer surface, as you can see here. This is true for a solid bar, but also for a hollow bar. This is useful to know because it means that hollow bars are way more efficient at carrying torsional loads, since the central part of a solid bar is only resisting a small part of the total load. Let's consider a small element within our cross-section that has an area equal to dA and is located at a distance ρ from the center of the cross-section. The internal force acting on this element is equal to its area, dA, multiplied by the shear stress τ. We can use this information to work out an equation for calculating the shear stresses. The moments caused by the internal forces acting on all of the elements within the cross-section must sum up to be equal to the torque T. Otherwise, equilibrium is not maintained. We can represent that mathematically by this integral. We know that the quantity τ divided by ρ is a constant, because the shear stress varies linearly with the distance from the center of the cross-section. So we can rearrange the terms and move τ over ρ out of the integral. It turns out that the integral we now have on the right is actually the definition of the polar moment of inertia, so we can replace it with the letter J, and we can rearrange this to get an equation for shear stress. The shear stress is a function of the torque T, the distance ρ from the center of the cross-section, and the polar moment of inertia J. It's quite a simple equation. So we now have equations that allow us to calculate the shear strains and shear stresses. We also have the equation for angle of twist that we talked about earlier. These three equations tell us everything we need to know about a circular bar which is under torsion. So far, we have only talked about a uniform bar fixed at one end with a single applied torque, but shafts are often loaded by multiple torques. This shaft, for example, which is supported by bearings at both ends, is driven by a gear at point B, and in turn drives two gears at points A and C. It is loaded by three torques. Before we can use the equations for shear stress, shear strain, and angle of twist that we just developed, we need to figure out the internal torque at each location along the shaft. The process for doing this is similar to calculating the shear force along a beam, which I covered in a separate video. First, we draw a free body diagram. Then we make imaginary cuts and use the concept of equilibrium to determine the internal torque at different locations along the shaft. This will give us an internal torque diagram that looks something like this. The maximum shear stress will occur in the section of the shaft with the largest internal torque, and can easily be calculated using the equation we derived earlier. I want to end the video by talking about failure due to pure torsion. If we have two bars, one made of a ductile material and one made of a brittle material, and we apply the same torque to both bars, we will observe that they fail differently. The ductile bar fails at an angle perpendicular to its axis, but the brittle bar fails at a 45-degree angle to its axis. We can explain this by remembering that ductile materials tend to fail in shear, and so fracture along the plane of maximum shear stress. But brittle materials are weaker in tension than in shear, and so tend to fracture along the plane of maximum tensile stress. Moore's circle for pure torsion looks like this. We can see that when our stress element is oriented this way, the shear stresses are at their maximum values, and we have no normal stresses. There is a 90-degree angle on Moore's circle between maximum shear stress and maximum normal stress, which means that normal stresses are at a maximum when our stress element is rotated by an angle of 45 degrees. This explains why brittle and ductile materials fail in different ways due to pure torsion. That's it for now. Thanks for watching, and don't forget to subscribe.
I hope the concept of torsion has become clear to you. So these people won't get their attendance also given in the middle of the class. Okay.